Okay, hi everyone. Welcome back to our statistics class notes, and we are on page 100, which is the last page of our section 7.2 notes. And I just want to summarize here what we found out from our 3 example simulations. So here's the things that we're supposed to get out of those. First of all, the estimator p hat, right? So the sample proportion we compute from each of our, running our samples over and over and over again. Each time we ran a sample, we got a p hat, we plotted it. We ran another sample, we got a p hat, we plotted, etc. 10,000 times of size 100 in the last simulation, 10,000 times of size 10 in the second simulation, and I just did a few of size 4 in the first one because it's just so small sample, it's not that interesting. All right, now the estimator p hat is unbiased for all sample sizes. Now, unbiased means that the mean of the sampling distribution will be the true population mean, the true population parameter, in this case p. So in other words, it estimates p accurately. The precision, the repetition of doing that estimation improves as the sample size gets larger. In other words, the standard error, right? The standard error, which is the standard deviation of our sampling distribution, gets smaller. The shape of the sampling distribution is more symmetric for larger sample sizes. The bottom line, increasing sample size improves precision. That's really important to remember. Now, finding bias in the standard error. The bias of p hat is 0. In other words, p hat is unbiased. There's a bunch of mathematics behind that. I'm not going to go over that, but just remember that means that it's estimating the true population proportion as we want it to. Now the standard error of p hat, remember, which is the standard error of the sampling distribution, the standard deviation of the sampling distribution we call standard error, is computed this way. And I'm not going to give you the mathematics as to why this gives you the standard deviation, but you need to know this formula and you'll use it over and over and over again. So it's the true population proportion p times the quantity 1 minus p, that same population proportion, divided by n, where n is the sample size. Then you take the square root of that. That gives you the standard deviation of the sampling distribution of p hat. Now notice that most of the time in real life we won't know our population proportion p. If we don't know it, then we plug in what we got as p hat from our sample here and it gives us an estimate for the standard error. But if we know the true population proportion p, which you will know in many of your homework problems, then you plug that in here to figure out what the standard error is of our sampling distribution. Okay, now the following conditions have to be met. The sample has to be randomly selected from the population of interest, and if the sampling is without replacement, the population must be at least 10 times larger than the sample size. So we'll always need to make sure our sample is random and that the population that we're pulling from is at least 10 times larger than the sample size. So back to our 5K runners. Let's assume we have 1,000 participants and 25% of them are walkers like we had in our last simulation and our second simulation also. And we're playing a survey in which we take a random sample of 100 people, so similar to our third simulation, and we're doing it without replacement. So we want to calculate the proportion of people in our sample who are walkers, as well as the standard error of our sampling distribution, and finally we would want to interpret those values. So what value should we expect for our sample proportion? Because the true population p is the center of our sampling distribution, we should expect that p hat is going to be 0.25 or 25%. Now will we get exactly 25%? Once in a while, but not always. It's going to be around that 25%. You saw that in the graph in the last simulation. Okay. What's the standard error? Well, since we know p, we're going to use that in our formula. So it's the square root of p times 1 minus p divided by n. So p is 0.25 times 1 minus 0.25 quantity, which is 0.75. If you can do it in your head quicker, you can do it that way. Divided by 100, the sample size. Take the square root of that, and I'm rounding that to 3 decimals right now. A lot of your homework asks you to do that, so I put it as 3 decimals, 0.043. Now, how do we interpret these percentages, these values? So what that means is about 68%, because we know our distribution is unimodal symmetric, so we can use the empirical rule. About 68% of the sampling distribution of p hat, is going to be within, this guy as a percentage is 4.3%, it's going to be one standard deviation to the right or left of what the population percentage of 25% is. So 4.3%, one side or the other, about 68% of our samples, right, of the sampling distribution of p hat, if I were to do over and over and over again random samples of 100 people, we only take one, but if I were to do over and over and over again random samples of 100 people, I plotted all the p hats I got, about 68% of those would be within 4.3% of the true population percentage of 25.